Okay, how do we know if a number is divisible by 4? The last 2 digits alone have to be divisible by 4, right? What about divisibility by 5?
Ends in a 5 or 0.
Ends in a 0 or 5. What about divisibility by 6? 2 and 3, right? Divisibility by 7 is a little trickier.
Double the last digits, subtract from the remaining if that's divisible by 7. That's divisible by 7.
Something crazy like that. I don't remember actually, to tell you the truth. Yeah, there is some kind of more difficult to remember algorithm for it. But I think just knowing like 2, 3, 4, 5, 6, 8, 9, and 10 is good enough. Okay, and all of those other ones are really pretty easy. So, okay, so this one is divisible by 3. So what you might want to do is divide it by 3, and then you'll get some number that's about 2,000 and something. And it turns out that I'm going to go ahead and factor the rest of it for you. You get a 31 and a 73. It's just 3 times 31 times 73. That's the number. So, with that in mind, what would you tell me about expressing this integer as a sum of 2 squares? If there's even one, this is actually quite different than the quadratic reciprocity law, which says that as long as there's at least one number of the 4k plus 1 form, you can flip the thing over with no sign change. Here it's different. This one says that all of the numbers have to be of the 4k plus 1 form, or else you can't do it, right? This whole thing is your little m, right? That whole thing is your square-free part. There's no square there at all. So this is impossible. Okay, so we can't even do that one. Yeah, Marissa?
Should we say something like 3 is of the form 4k plus 3, so...
Yeah, you should give a justification.
Okay.
Yeah, I'm sorry, I'm not being a good test taker here. If you just write impossible with no justification, that's not so good. I would just say something like, all primes have 4k plus 3 form, and I've labeled what m is. I think that would clarify it greatly. So every one of those primes is of the 4k plus 3 form. I'm sorry. I'm sorry. No, there exists a prime of. Sorry, I meant to say there exists a prime of the 4k plus 3 form. There we go. Actually, you can just say it's just the first one, 3. That's already a problem right there. Yeah. Okay. So any number that's divisible by 3 but not by 9, you would have this problem for. Okay. It's like 27. Same problem. 27 would be, 3 squared times 3. There's the little m right there, right? So you're in trouble. Okay. How about any odd perfect number? Just to tie it in with something else. So let's take any odd perfect number, I'll just call it little n here. Suppose we want to express that as a sum of 2 squares. And by the way, we don't have an example of such a number, because we don't know if such a number even exists. But if such a number exists, we would like to show that it either can or can't be expressed as a sum of 2 squares. Does anybody remember the form of an odd perfect number? P1 to the K1.
P2 to the 2j to the
And so on, right? I think this is one of the theorems, right, in the list. So if I ask you this theorem on the test, and this shows up, you can always go to the, because I'm going to print the theorems out on the back of the exam, so you're going to get that information. You can just look at it if you don't remember how the theorem is stated, right? You can express n that way if you have an odd perfect number. And what are the other conditions here?
P1 and K1 are
Okay, P1 and K1 are congruent to 1 mod 4, right? 1 mod 4, thank you. P1 and K1 are congruent to 1 mod 4, exactly. So here's the thing. all of this part that starts with the second prime is actually a perfect square, right? So you can think of this as P1 to the K1 times, you know, the perfect square of P2 to the J2, P3 to the J3, and so on, up to PR to the JR. Okay? So this whole thing here can be thought of as the capital N. Now, there could be, this K1, for example, could be equal to 5. If K1 is equal to 5, then really you should be putting 4 of those P1s inside of here as well. Okay, but at any rate, the capital N at least includes that whole perfect square part, right? So you can actually, if you wanted to, you could write K1 as 2J1 plus, actually you could just write it as, sorry, you could just write K1 as 4J1 plus 1. It's 1 more than a multiple of 4, right? K1 is congruent to 1 mod 4. So I could write K1 in this form. And if I did that, I could actually then keep one of my P1s on the outside and put the rest of them on the inside. So this would be P1 to the 2J1, P2 to the J2, dot, 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 PR to the JR, all of that squared. Let me give everybody a chance to look at that. I've actually tried to really make it more clear. So instead of this being the N, this whole thing now would become the N that's being squared. Look at the power of P1. What power is it? 2J1, but I'm squaring that, so that's 4J1, and then plus 1. It's that form right there, right? So that's P1 to the K1. So, P1 itself has the form 4K plus 1, right? So is this possible or not?
Yes.
It is possible. There are no primes outside of these brackets that have the 4K plus 3 form. So I know that I can do this. This is by a theorem that any prime of the form 4K plus 1 can be written as a sum of 2 squares. So you can just write it as a squared plus b squared and then times n squared. Okay, and then that, of course, can be combined together, and it forms an squared plus bn squared. So it would end up looking kind of like that. Okay? All right. Does that make sense so far? Okay. So let's, there's more examples of that in the review packet, the practice packet, but I'm going to probably not go to the review packet because I'm still doing problems from here right now. Okay. Okay, let me see where I want to go to next. I did that, I've done a lot. Okay, let's just do number, what number am I on, 7? I've kind of gone off of the order of my packet a little bit here, but that's okay. Let's compute 12,111,009 to the 8,765th power modulo 4,321. Okay. Please don't bring your supercomputer to the final. Your little handheld calculator probably won't like this too well. So, suggestions what to do?
Fine.
A to the, so we're taking a, that was the whole point of asking you this problem, is because I have not talked about that yet today. The Euler's theorem, which says that A to the phi of n is congruent to 1 mod n. This is as long as the GCD of A and n is 1, right? Now, in order to figure out what phi of 4321 is, what am I probably going to need to do? Figure out the factorization of it, right? I would have to factor it. So that's one of the first things that you would want to do here. 4321, I'm going to help you with the factorization again. Turns out it is not that simple to factor it. The smallest prime that goes into it is 29, as it turns out. And that gets multiplied by 149. Okay, so this is the factorization. So actually what you could do is you could calculate this number mod 29, calculate it mod 149, and then again use the CRT. Okay? Guys, you don't have to do that. You can leave the original mod, and if you do that, then you're just going to be figuring out, you know, phi of 4321. Well, that's going to be, remember that phi is multiplicative. Phi of 29 would be 28 because it's a prime. And 149 is also a prime, so this would be 148, and you could work that out, okay? But I almost always would advise you, to work with the smallest mods that you can. Even though you're going to make two problems out of it, you're going to have to do mod 29 and mod 149. It's just better to have smaller numbers if at all possible, okay? So I'm going to recommend that we look at 12,111,009 mod 29. It turns out that if you divide by 29 in your calculator, you're going to get 0. So this number is actually a multiple of 29 already, okay? And then in mod 149, again, with a calculator. So these are calculator, you know, simplifications. Mod 149 is congruent to negative 9. Okay. So obviously now if we raise both sides to the 8,765, right, we're going to get, so we're going to conclude that 12,111,009 to the 8765 is congruent to 0 to the 8765, which is 0 mod 29. So I know what my number, you know, if you want, you could just call this thing x. I know that x is congruent to 0 mod 29. All right, x is congruent to 0 mod 29. And I know that, let's see, mod 149, so x is congruent to negative 9 to the 8765 mod 149, right? Like that. And yeah, using the Fermat's little theorem, or in other words, so whenever you're reducing a big power of a number, I do know negative 9 is relatively prime to 149. So when I raise it to the 148 power, I have to get 1. So I can take out 148 powers of negative 9. Turns out there will be 58 of those, and then you'll be left over with 33 more of them. Okay, so this is just the division algorithm. I just simply take 8765 and I divide it by 148. I get a quotient of 58 and a remainder of 33. Okay. Does that look right? What's 148 times 58?
8,584.
And what do you get when you add 33 to that? Oh, is this supposed to be 59? This is 59 here? Oh, that's a typo. Oh, gosh. But that's okay, because, see, I'm actually using somebody else's notes, so I can blame somebody else for that. Yeah, so there you go. So that looks more reasonable. I thought it looked a little bit off. Anyway, it ain't going to matter, because negative 9 to the 148 is what? 1, right? In mod 149, it would be 1 by Fermat's little theorem. So this is 1. by Fermat's little theorem, or of course you could use the Euler theorem. You could just refer to it as, remember, Euler's theorem is just a generalization of Fermat's little theorem. Right. Okay, so we just get negative 9 to the 33 mod 149. And now we just have to figure out how to reduce that, okay? So it turns out that if you take negative 9 and you cube it, so negative 9 squared is just 81. 81 is not particularly simple relative to 149. But if you cube the negative 9 and then raise the result to 11, negative 9 cubed actually comes out to 16. So you'll get 16 to the 11th here. Okay? And you can just keep reducing this thing. 16 squared, that's going to be 256, right? Would be then raised to the 5th with another 16 on the end of it. 256, well, relative to 149, that would be 107. So 107 to the 5th times 16. So you just start playing around with your calculator for a while. 107 to the 5th, now you can probably put that in your calculator. And the final answer, when you simplify this, comes out to 30. So if my notes are right, which I hope they are, it comes out to 30 at that point. So x is congruent to 0 mod 29, and x is congruent to 30 modulo 149. And now you have a Chinese remainder theorem application that you can do. And I think I'll just put dot, 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 dot here. Okay, so you can check on your own with the CRT. Check that with the CRT, that's going to come out to x congruent to 1073 modulo 4329. Okay? Does that make sense, guys, so far? Okay. Can I do one or two more, or have you guys had enough? Do a little bit more? Why not, huh? Is that okay? All right. I have just a little bit more here, not much. That particular last problem was just to show you, you can do high power calculations by using the Fermat's little theorem and the Euler's generalization theorem to reduce the numbers down as you go. And breaking up the primes again allows you to use the CRT. Okay, so more of the same old thing. Okay, so this is number 8, is it? Number 8. For which primes p greater than or equal to 7 does the Legendre symbol of 15 with respect to p equal 1? Okay. So we'd like to know, basically, under what circumstances is 15 a perfect square? Modulo which primes? Anybody have any thoughts on that? Okay, the 15 splits up as 3 and 5, right? So, there's going to be two cases. What are your cases that you're thinking of, Davey?
P is equal to 1 mod 4 and 3 mod 4.
Okay, so we may get into that, but before I get into that, I just want to think about, as you say, the splitting up the 15 part.
So 3.
Yeah, so the 3, basically, in order for this Legendre symbol to equal 1, right, you either have to have both of these equal to 1, or you have to have both of these Legendre symbols equal to negative 1. Okay, so that's kind of what I was looking at, thinking of it that way. Okay, so let's think about it this way for now. So let's just look at case 1. Okay, so case 1, maybe within case 1, we can now look at the case A and case B that Davey was just suggesting. Does that sound okay? So if we take this first case, let's look at case A. P is congruent to 1 mod 4. Okay. And then case B will be P is congruent to negative 1 mod 4. So let's look at the first case. So suppose that we want both of these to equal 1, and we know that P is congruent to 1 mod 4. What does knowing that P is congruent to 1 mod 4, how does that help us?
We can flip it and just leave it.
Okay, so we can flip these and leave them the same, right? So